Greetings, fellow conscious remnants of the Big Bang. I'm Zane, this is the Biomechanic. Alright, we're going to jump straight into things here on the channel with the topic that over the years I've seen students struggle with the most. Okay, let's consider this barbell in front of us. One end of it is inserted into a T-bar row, which means it's able to rotate. And the other end has a 20 kilo plate attached to it. So what we formed here is a lever. The lever itself is the length of the barbell. Just like if we were talking about in the human body, a lever would be a bone. Down the left-hand side where the T-bar row is, that's our point of rotation, so that's what we call the fulcrum. So to have a lever system, you need to have a fulcrum, a point of rotation, then you need to have the lever itself, which is the thing that's going to rotate. So our friend gravity here is always acting upon the levers in our body. The good thing about gravity is there's absolutely zero mystery here. It always acts completely down, so perpendicular to the ground, and it always accelerates things at 9.81 meters per second squared. So that will become relevant soon when we start to do our calculations. Okay, so what I want you to do now is just think for a moment. If you wanted to lift this lever and you wanted it to be the absolute easiest thing you've ever done, whereabouts on this lever would you grab it and exert your muscle force? I'm going to assume that most of you will say that you'll grab it at this point. If you said that, great. That means you have this intuitive sense about how a lever system works. If you said that you would have grabbed it here on the other side of the barbell, that's also a pretty decent answer as well. You might have said this because you often see people in the gym doing T-bar rows in this exact position. What I will wager you've never seen is somebody trying to lift that 20 kilo plate from all the way down here. I think you probably guessed that that would be almost impossible. For the sake of this lever problem that we're talking about now, I'm only considering the weight of the 20 kilo barbell all the way down the other end of the lever, but we also have to remember that the lever itself has 20 kilos of mass. So trying to rotate that barbell from the position of this red arrow would be, I would say, impossible. Even for the strongest person, that would be very difficult to do. So when we're talking about levers, it's really important to understand the different arms that are involved in a lever problem. So the first one is the resistance arm. This is the distance between the fulcrum and where the force of the resistance is applied to the lever. The second one is the effort arm. So this is the distance between the fulcrum and where the effort is applied to overcome the force of the resistance. So obviously when we talk about human movement, this effort arm is going to represent the force of muscle. This is the point at which the muscle will attach to the bone and you'll get rotation to occur. Now, when we arrange these things in this particular order, so the fulcrum on one side, the resistance towards the other end of the lever, and then the effort in between the fulcrum and the resistance, we end up with what we call a third-class lever. So the thing about a third-class lever is that you will always have to exert more force than what is being exerted by the resistance. Now, the thing about a third-class lever is you're always going to have to exert more muscle force than is being exerted by the force of resistance. So if we said, just to make the math really simple, that's a 20 kilo plate on the end of the bar, and you're slightly closer towards the fulcrum than the plate is, you're going to have to exert more than 20 kilos of force to overcome that and get the barbell to rotate. And we describe that as mechanical advantage. So mechanical advantage can be calculated by taking the effort arm and dividing it by the resistance arm. And so I've chucked some numbers on here for it to make sense. If we take an effort arm that is 1.3 meters long, and we divide it by the resistance arm at 1.5 meters long, we get a mechanical advantage of 0.87. So while not horrendously lower than 1, it is still definitely lower than 1, meaning you'll have to exert more muscle force to overcome that resistance. Now, if we switch things up a bit, if we go and grab that barbell from the very first place that kind of made the most intuitive sense to make it the easiest, then now our effort arm is longer than our resistance arm. And what we've done by rearranging this is change the class of lever. So now we have our fulcrum to the left as we did before. Then the furthest thing away from the fulcrum is the effort arm. So this is the muscle force being applied, which means that our resistance is now between the fulcrum and the effort, meaning it's a second class lever. Now, second class levers are where it's at. If you think about a wheelbarrow, you have the fulcrum or the wheel down one end, you have your muscle force down the other end picking up the handles, And then you have everything you're carrying in between the wheel and yourself. That's the resistance or the load. So let's look at these numbers. If we now divide the effort arm 1.8 meters by the resistance arm of 1.5 meters, we get a mechanical advantage of 1.2, so greater than 1. So what that means functionally is whatever the resistance force is, you don't need to apply that much force to get it to lift, to get it to rotate. So if that plate is 20 kilos, then you need to apply less than 20 kilos force to rotate that. And I will note now for anyone that's paying attention, when we talk about force in levers, we're not going to use kilograms, we'll use newtons, but we'll come to that soon. So when we apply force to a lever and we cause that lever to rotate, what we're generating is torque. So torque is the rotational application of force. It's a pretty simple formula to work with to figure it out. It's just force times distance. And when we talk about levers, we're talking about the distance of the moment arm. And so the moment arm, this is this mystical, magical thing that quite often stumps students, but I'm going to try and make it as clear as possible. A moment arm is the distance between the fulcrum and the force vector intersecting at a right angle. So that might sound a little bit confusing, but try and memorize that as best as you can. And so in this schematic of the barbell problem that we've been looking at, the fulcrum is down one end. The green arrow represents the force of gravity. So the force vector of gravity always going straight down. And so where the green arrow is interacting with the barbell, that's where the 20 kilo plate would be. So that distance between the fulcrum and the green arrow is your moment arm. It's that distance intersecting the force at a right angle. So what happens as we start to rotate the barbell? Okay. Well, previously when we looked at the barbell was parallel to the ground. So that meant that the moment arm and the resistance arm were equivalent. There was no difference. But as soon as we start to rotate the barbell, that relationship changes a bit. So you'll notice that the rules of a moment arm are still the same. It's still the right angle intersection between the fulcrum and the force vector. But what is changing now is the distance. The distance is reducing as the barbell rotates. And the higher it gets, the shorter the distance. Now, for the eagle-eyed observer, you'll notice that what's happening as we rotate the barbell is we're creating a right angle triangle. That's going to become very relevant very soon. But for the moment, let's just stick to the concept of the resistance arm and the effort arm being the moment arm. All right, well, before we try and figure this out, there's a bit of housework we have to do first of all. And that housework is we can't use kilograms in a lever equation. We have to convert it into the SI unit for force. Kilograms is an SI unit, but it's the unit for mass. What we want to understand is what happens to that mass when we expose it to the acceleration of gravity, which is 9.81 meters per second per second. So to get our Newton value, we just have to multiply 20 kilos by the acceleration of gravity, and that gives us a Newton value of 196.2 for that plate. So if torque is force multiplied by the distance of the moment arm, then this equation is pretty simple. The torque of resistance, that is the torque generated on the lever by the plate, is equal to 196.2 newtons multiplied by the resistance arm of 1.5 meters. So that gives us a torque of resistance of negative 294.3 newton meters. So I guess the first thing you're asking is, why is it negative? Well, if it's a clockwise torque, as it would be if the floor suddenly disappeared and the barbell was to rotate, that's designated as a negative torque. Any counterclockwise torques are labeled as positive. All right, so how much muscle force do you then need to generate at that point in the barbell, grabbing it by the end, to overcome the torque of resistance, which is negative 294.3 newton meters? So if we just multiplied force by distance to get torque, and I want to find out how much force I have to apply at a different distance to overcome that torque of resistance, what do I need to do to this equation? I need to rearrange it, obviously. If the resulting unit is Newton meters, and I want to arrive at a Newton value, then I need to rip meters out of there. I need to divide that number by meters. So once I take a value that is in Newton meters and I divide it by meters, I've essentially gotten rid of the distance component, and all I'm left with is force. So I'm going to divide that negative 294.3 Newton meters by the distance of the effort arm now. And that effort arm, as you know, is greater than the resistance arm. So when you divide that 294.3 Newton meters by 1.8 meters, we end up with 163.5 Newtons. So that's saying that you need to exert 163.5 Newtons of force to get that barbell to rotate, which is definitely less than that force of resistance. And that's the advantage of a second class lever. You don't have to be as strong as the amount of force that's being exerted by the resistance. Okay, so let's now grab the barbell at roughly the place where anyone doing a T-bar row would do it. And it's the same calculation. So it's our torque of resistance, our negative 294.3 Newton meters, divided now by 1.3 meters, which is the distance at the effort arm. And we arrive at a Newton value of 226.4 Newtons. So we can see here that it's definitely more than the force of resistance, but it's not so much that it would be terribly hard to do. So if you only had one 20-kilo plate in your gym, and you were able to do 10 reps of a T-bar row at that position quite easily, and you want to try and get stronger, you don't want to keep increasing reps forever, but you don't have any more weight to add onto that barbell, what would you do to increase the muscle stimulus? Well, hopefully everyone's realized by now that to do that, all you have to do is go towards the fulcrum. So the closer you go towards the fulcrum, the more you decrease the effort arm, you're also decreasing the mechanical advantage. So that 20-kilo plate is going to feel heavier and heavier the further away you get from the force of resistance. All right, now we come to the heart of the problem. We want to understand what happens when we try and grab a third-class lever from just in front of the fulcrum. So when we have a very tiny effort arm versus the resistance arm. And of course, we're building up to something here. This is going to become very relevant quite soon. Okay, all we have to do is just change the numbers we plug into that equation. If we take our force of effort of negative 294.3 Newton meters and we divide it now by our tiny effort arm of 0.15 meters, we get 1,962 Newtons of force required to rotate that barbell. And that's equivalent to 200 kilos of weight force that you have to generate to lift that 20-kilo plate at that distance. That's not even factoring in the weight of the lever itself. So to be able to rotate this lever system that close to the fulcrum would be incredibly difficult. I'd personally love to see someone do it. Well, I hope you enjoyed that. That's just, there's going to be plenty more with that. Don't, and I'll see you back here on Biomechanic.